Hi everyone, I'm back with the new episodes of ransomware analysis series, and today I'm going to tell you about how to unpack Buran ransomware. We'll try manual unpacking with the help of Scylla and Reconstructor, as well as a tool by Hasherizada called PE-sieve. First step is static analysis, so let's open Buran Ransomware PID to find out if there is any packer and what is the compiler. And as you can see, nothing found. So if we run deep scan, so it says Buran Ransomware is compiled by Microsoft Visual C++. In fact, Buran Ransomware is written in Object Pascal and compiled in Borland Delphi. And supposedly the protector's code is written in Microsoft Visual C++. Therefore, the first step, we need to unpack Buran ransomware. And to do that, we open it in IDE and start on the debugger. Also, for dynamic analysis, we start process monitor. So we set a filter for Buran.exe process. So let's start our debugger. In the first run, we'll just resume the process and try to see what will happen. The first problem, we see that the application generated unknown exception called 5. So in process monitor, we can see that it just loaded modules to the process. To understand where it happened, we can open stack trace window. In stack trace window, we can see that the exception was generated by WinStation query information function from winsta.dll. And this function is called from this place in Buran. So I'm going to set up breakpoint. If I move a little bit up, you can see there is a block responsible for runtime linking. So here it loads winsta.dll library and gets the address of the WinStation query information call. So I'm going to set breakpoint here as well. What this function is about. The MSDN articles that we found tell us that the purpose of the function is determining whether the calling application is running on a remote desktop connection RDC client, and there is an important note for us that this function only works reliably on Windows 2000. I have a question why the ransomware authors they use this function in the code. So the answer is that this is a kind of obfuscation. So they added junk code that works not reliably, generates exceptions, and complicates the debugging and reverse engineering. So let's continue and pass the exception to the application. So here we have a jump. So the module is loaded. And again, we get the address of the process. Continue, and we see again the function is called. And again, we have exceptions. We don't want to run it in the loop. Therefore, we want to see where the end of the loop is. Well, supposedly we have this jump. We don't go again to the next iteration of the loop, so we can set up our IP to the instruction to where another branch goes. And again, we resume the application. And we can see that it created the process. The application name is ctfmon.exe, but this is a fake application. It's not original Windows ctfmon application. There is also argument sent to this application, asterisk, after preliminary analysis, I know that it checks for any argument. It doesn't matter what particular string you are going to pass to the application. It requires only the fact that there is something as a command line argument. And then we can allow or block the application. So let's see what will happen. So if we open Process Explorer, we'll see that we have a new instance of ctfmonexz fake process, and if I try to suspend it, I have no privileges to do that, and therefore I need to restart my Process Explorer as administrator. So I will have permissions to suspend or stop the process. So I suspend ctfmon and go back to process monitor. So first let's take a look at this process create instruction. So the first one starts command line. So let's see what is the string for command line. I want to see it in Notepad. So here we have command line, then we have copy operation, then we have adding the reference to ctfmon.exe to autorun key, and finally what we have here is starting ctfmon with asterisk as a command line argument. Let's go back to IDE and start debugger again. Now we know that we need to set up a breakpoint in shell execute function. Shell execute is located in shell 32.dll. So we set breakpoints in different version of the function. And now we can start our program. So we have again exception here. And so we want to escape from the loop with exceptions. Therefore, we set IP out of the loop and resume the application. So now we are inside of the shell execute function. The return address is another shell execute function, but we can again open stack trace to see where shell execute function is called. And here you can see that there are two places in the code that are in the call stack that have no module name. So this is supposedly code of Unpacker. And finally, from Unpacker, it jumps to the Buran code. We can double click and we go here. So this is a place in Unpacker's code. You can see this is a debug 038 section, which calls the address in EAX. And this call supposedly will lead us to original entry point. But the thing is, we can't set up software breakpoint here. We need to find out where the the buffer for unpacker's code is allocated first, and then add offset for this function and set up a hardware breakpoint to this address. We need also to set breakpoints at virtual alloc functions, because they are used to allocate the buffer where the unpacker will be loaded. So we'll get the base address of the unpacker, then we add the offset for this function, and finally we'll be able to set up a hardware breakpoint. So we open kernel32dll, find the virtual alloc function, set breakpoints here, and restart our application. So we have again this junk code for Win station query information, and now we get an exception. We pass it to application, then we go to the end of the loop, and next we'll jump out of the loop and continue until we get the buffer allocation for unpacker. So here we are, then we get out of the function, and EX contains the base for the unpacker's code. So in our example, this is this address, and then we can add the offset for the function that calls original entry point. And we need to go there and need to set up a hardware breakpoint. So you can see by default, when I have no code here, IDE proposes to set a hardware breakpoint. So I said OK, and then I resume application. And here we have a call, and EX should contain the original entry point. So we go by the call, and here it is. And now, when we know address of original entry point, we can start unpacking using import Reconstructor or Scylla tools. To do that, we open first our tool, we select process that is under debugger currently, and if we click search import address table, the tool says it found it, but when we get imports, we have actually 0 valid APIs shown in the imports panel. So therefore, we need to get the original entry point and send it to the tool. Now we have another variant for import address table, and when we get them, so finally we can see the list of valid functions, and we can check, for example, if we have a shell execute function, because if we open IDE and open imports tab and try to locate shell execute, so we can find it. This import address table is incorrect, and many functions are loaded during runtime. So next we need to take dump. So okay, and fix the dump using import address table. So here we have the unpacked sample. Let's start it to check if it works. Windows tells us that this sample can't run on this PC, so supposedly the reconstructed PE file is wrong, so we need to fix it manually. Let's try to do the same using import Reconstructor. Scylla is a new version of import Reconstructor. It is based on import Reconstructor. And here again, if we click auto search, it says like I can't find anything good at this original entry point, therefore we need to specify OIP that we found. Moreover, we need to remove base image address. And now we can search and it found it. Then we click get imports. And again we have a valid list of APIs. So again we open, we can see there is a shell execute function here. And now we need to fix the dump. So we can use the same dump that Scylla took before. And we have the reconstructed unpacked version of the Buran ransomware. Let's try to open, and we have the same problem. This application can be run. So let's try to figure out what's wrong with the PE format file of the file. So we open it in PE view. There is an error. Some of the data structures cannot be viewed. We have numerous resource data entries, and they are not inside of the resource section, but they are drawn in the tree as a root entries. So there should be image resource directory entry first, and then from in this directory we can add these data entries. So this structure is wrong. Then we have resource section, which has address offset in the file, but no content, which means the size of this section is 0. And we have another section which has no name, and it points to the same file offset, and it has some resource data. So this is the first problem. And the second problem that I found during analysis of this incorrectly created unpacked file is when we go to optional header, the import table has a wrong relative virtual address, which is here 38000, and our import table is stored here in iData section, which stands for import data section, and here we have another RVA, which is 31000. So that's all fixes that we need to do. We open our unpacked file in Hex Workshop, and let's start fixing our file. So we need to locate where the resource sections start. It's 2DE00. So we find this place here, and we should remove the resource data entries. So we just we're going to fill it with zeros, and we'll see if it works. Our resource section here, and we can remove this extra section because both resource section and section without name points to the same file offset. They're actually the same. And we go to section header, and here we have 0 raw size of raw data and 0 virtual size. So we can take the size from unnamed section, which is 1400. It's raw data, and this is the virtual site. It's enough to set the raw data size, and we will put this value here. So the offset in the file is 348 in hex. So we go to 348 in hex. So this is the value that we're going to fix, and it will be 1400. So next, change the number of sections. So this can be done in file header. Number of section, here we have 10, so 9 will be enough. This is offset in file 106. So that's it. So we change it to 09. And finally, we need to fix in optional header, we need to fix the address of the import table. So the offset is 180. So here it is. So now it's 3800. So we need to fix it to 310. We close it here to unlock the file and save it. As fix it. It starts a new instance from the users folder under ctf-mon.exe name. This was the long way how we can manually unpack the sample. Well, there is another way which can be much more efficient. So we were going to use a PE-sieve tool by Hashirizada. So let's open the command line. Go to desktop. So here we can see the help for command line. So the tool has only one mandatory parameter, which is a process ID that points to the target process that we want to dump and fix the import table. Then there is another option /imp, which is if we specify it, it will help us to recover the import address table. And there are two options for that. So the tool can recover erased part of the partially damaged import table or build the import table from the scratch based on the found IAT. We can also use auto detect. So we need to specify one, and the tool will automatically detect which mode will suit the best our needs. So let's try. PID of our process is, let's find it here, it's 4076. And I specify auto detect for import reconstruction. And finally we have a folder. So here we have a text report for the found imports. Let's take a look what we have here. Well, it seems like it is correctly found my import table. So let's find the shell execute. So here it is. And the last thing we need to check if it works. It restarts itself as a ctf-mon.exe. In this video, I showed you how to prepare malware for analysis. So we unpacked Buran Ransomware, we followed two approaches. The first approach is the approach of paying or manual unpacking. So we debugged manually, found original entry points, and used import Reconstructor or Scylla tools to dump and reconstruct the import address table. And the second approach is easy way to do unpacking is to use a PE-sieve tool by Hashirizada that created unpacked version like in a matter of seconds. So that's it. In the next episodes, I'm going to explain the encryption model of Buran ransomware, and then we'll proceed to creating Decryptor for Buran ransomware. Thank you for your attention.